Hello everyone and welcome back to the binary search series, and this is problem number 3 in this series. And in this video we will discuss binary searchable elements problem. Now according to me this problem is really important because this problem actually tests your understanding of the very core concept of binary search. So if we are able to understand this problem and if we are able to solve this problem, then we will get a very good understanding of the core concept and intuition of binary search. And one more thing, I have picked this problem from Geeks for Geeks. So I think this problem on lead code is locked and you need a premium subscription to unlock that problem. And since I did not have the premium subscription, I'm solving this on Geeks for Geeks. So let's get started with the problem. First, let's read the problem statement. So it says binary search is a search algorithm usually used on a sorted sequence to quickly find an element with a given value. In this problem, we will evaluate how binary search performs on data that isn't necessarily sorted. An element is said to be binary searchable if, regardless of how the pivot is chosen, the algorithm returns true. And then we are given example, and the ask in the problem is given an unsorted array of n distinct integers, return the number of elements that are binary searchable. So before jumping to the question, let's understand or let's quickly discuss the very core concept of binary search. So given an array, say a comma b comma c comma d, what is the very core concept of binary search, or why does binary search work? I know that binary search works because if I pick an element as the pivot and I compare my target with this pivot, I know the exact side where I need to move or where I need to continue with my binary search. I can exactly determine that whether I need to continue my binary search on the right or my binary search on the left, and accordingly I can discard the other half of the array. This confirmation is kind of the very core concept of binary search, because if we would have not been able to confirm the side where we need to continue with our binary search, we would have not been able to discard half of the element, and then we would have landed up with an algorithm with a much worse time complexity. So this is the very core concept, that at every step we are sure that in which direction we need to move. And again, why are we sure in which direction do we need to move? Because it is given, or it is a prerequisite for our binary search, that our array is sorted. And since our array is sorted, we are able to make sure that we are moving in the correct direction. Now, what does the question say? It actually says that we are given an array. So we are given an array, suppose 2 comma 1 comma 4 comma 8 comma 7. Now the input array which is given to us, in this case 2 comma 1 comma 4 comma 8 comma 7, may not necessarily be sorted. So we can see that our example array is not sorted, and that's what the question says, that our input array might not be sorted. So if I try to perform binary search for 4, or if I try to perform binary search for 1, will I be able to find these elements after applying binary search? And just a little variation here is that regardless of how the pivot is chosen, the algorithm returns true. So we are not always picking the middle element as the pivot. We can pick any element as the pivot. So let's assume that pivot is chosen randomly in every iteration. So if the pivot is chosen randomly and we are trying to search for, will our binary search give us the correct answer? Will it be able to find 4? If we are trying to search 1, will our binary search give the correct answer? So what we need to do in the question is that we are given this input array. We'll be given an input array of integers which might not necessarily be sorted, and we need to determine the number of elements we'll be able to find using binary search. So, or in other words, if we pick each element and try to do a binary search on this array for that element, that element will be found? And so we have to return the count of such elements which will be found using binary search, irrespective of the fact that the given array is not sorted. So let's try to analyze that. How will we find the elements which we will find irrespective of whether our array is sorted or not? Now let's pick an element 1. So if we are trying to find 1, and now let's analyze the different cases, or the different pivots that can be picked. So if in any iteration I'm picking a pivot which is on the right side of 1 in this array, so I'm picking any of these elements as the pivot. So pivot as we discussed, that pivot will not always be a middle element. We can pick any number as the pivot, not necessarily the middle element. So let's assume that we picked any number out of these number as the pivot. So for my 1 to be found in binary search, what I need to make sure is that my 1 is in the correct direction of every pivot. So now that I'm trying to find 1 and I'm picking any of the elements on the right side as the pivot, I need to make sure that in my binary search I'm always discarding the right half of the remaining array and I'm moving on the left side with my binary search. Because if I'm moving on the left side, then only I'll be able to find 1, because 1 exists on the left side of this pivot. Because if I discard the left side from any of the pivot, I won't be able to find 1. Now the condition in which my binary search will move to the left side and discard the right side will be if my 1 is smaller than the pivot, then only I discard the right side and search the left side. Now for any possible pivot on the right side, my 1 should be smaller than all the pivots, because for all the pivots I should move on the left side. If there's a number, say -1 here, and I pick -1 as the pivot, now when I compare 1 and -1 as the pivot, I will discard my left side and move on the right side, which is wrong. We always have to discard right side and move on the left side so that we'll be able to find 1. So for 1, any element on the right side should actually be greater than 1. Then only we'll be able to move to left. And in that case only, if we pick any element on the right side as the pivot, we can make sure that we'll be able to find 1. And the similar logic can be extended to the left side as well. So for any element that is on the left side, in this case 2, so for any element on the left side and we are trying to find 1, all the elements on the left side should be smaller than 1, because if all the elements on the left side are smaller than 1 and then we pick any element as the pivot, we will always move on the right side and discard the left half, and that is the correct direction. We want to move in the right side because 1 actually exists on the right of all these pivot elements. And if I'm picking any element as the pivot and I want to move on the right, these pivot elements should actually be smaller than 1. So what I can conclude from our discussion till now is that if I pick any element on the right side as the pivot, to move on the left side, all these pivot elements should be greater than the target element, and to move in the correct direction from the left, if I pick any element on the left side as the pivot, to move on the correct side, that is right side, all these pivot elements should be smaller than the target element. So if we are able to make sure that all the elements on the left are smaller than the current element and all the elements on the right are greater than the current element, I can make sure, irrespective of what pivot is chosen, I will always move in the right direction and my algorithm will be able to find my target element. So that is the whole logic behind this question. So let's try to see for an example. Let's take an example 2, 1, 3, 4, 6, 5. Now let's pick 3 as my target example. So if 3 is my target example and I say in my first iteration I picked 4. If I picked 4, I will discard this array and I will also discard pivot as I always do, and I will be remaining with this particular array. Now let's say we randomly pick a pivot and the pivot we picked was 2. Now if the pivot was picked as 2, I know that my target 3, which is greater than the pivot, will obviously exist on the right side. So that is the logic of binary search, right? We always assume that the greater element will be on the right side, so we discard the left half, and the smaller element will be on the left side, so we discard the right half. So 3 is greater than 2, so we'll discard the right half as well as we'll discard the pivot. We will discard the left half and as well as we will discard the pivot. So there's no left half here, we'll only discard the pivot. So the remaining array is this. Now let's assume that my random pivot picking logic picked 1 as the pivot. So if I have picked 1 as the pivot, I know that 3 is going to be on the right side. So I will discard the pivot and the left half. So there's no left half, I will just discard the pivot, and the remaining element is 3. So I was able to find 3, and the only reason I was able to find 3 was this, because all the elements on the right side were greater and all the elements on the left side were smaller. So now the problem reduces to just checking that are all the elements on the left side of the current element smaller, and are all the elements on the right side of the current element greater than the current element. If these two conditions hold true, then this element will be found using our binary search logic, and then we can do a plus plus in our answer, or the count of the numbers which will be searchable in this unsorted array. Now, how are we going to do this? How are we going to solve this problem, or solve this problem statement? Now, let's assume. Now, in this case, we discussed that how 3 will be found. Let's assume a wrong case where the number might not be found. So let's assume 1. So as we can easily see that 1 is in wrong place, because 1 is actually less than 2, but still it is on the right. So there's an element on the left which is greater than the current element. So this should not be searchable, and it is very easy to find. It is very easy to prove. So we assume that our random pivot picking logic pick 2 as the pivot. Now if 2 is picked as the pivot, it will compare, and based on our logic of binary search, uh, it will discard the right half, because 1 is smaller than 2, so it will think that 1 will be on the left side, so it will discard the complete right half and the pivot as well. And we'll see that since after this step my size of the remaining array will be 0, so I will say that I did not find 1 in the binary search, while 1 was actually there. So the only reason 1 was not found was that because one of the two conditions that we specified was not followed. Now again, how are we going to check these two conditions very efficiently? So we kind of do something as a precomputation. So we traverse from right to left, and as we traverse, we keep a track of what was the minimum element up till now. So if we keep a track of what was the minimum element up till now, and my current element is actually smaller than the minimum element, so I can make sure that my current element is going to be smaller than all the elements. This is pretty obvious, right? Because the minimum element, what is the minimum element? I've seen all the elements till now, and this element is actually the smallest element in all the elements I've seen till now. Now if my current element is equal or smaller to the smallest element I've seen up till now, then definitely my current element is smaller than all the other elements. So using this logic, we will try to do it very efficiently. So what we'll do, we'll traverse this array from right to left, and what we'll do, we'll try to keep a track of the minimum element up till now. So up till when I'm at the last index, up till now the minimum element is 6, and my current element is equal to the minimum element, so that is there. But right now we'll not do this computation, we'll not check this condition, we'll just store that for each index what is the minimum element up till now. So here it will be 6, here the minimum element up till now will be 5, here the minimum element will be 4, here the minimum element will be 3, here the minimum element will be 1, and for this index the minimum element again will be 1. So this will be our pre-computed array which actually stores the minimum element up till now. Then we will have another array stores the maximum element up till now, and we'll store the maximum while traversing from left to right. So we'll traverse from left to right, and for each index we will store the maximum element up till now. So maximum element at my first index is 2, then maximum element at this index is again 2, maximum element here is 3, 4, 5 and 6. So now I have a track of maximum element from the left to this current element, and I have a track of minimum element from right to current element. Now what I need to do, I just need to do a single traversal, and for each index I need to check that my current element should actually be equal to the minimum element from right, and my current element should actually be equal to the maximum element from right. If any of the condition does not satisfy it, that would imply that there is either a smaller element on the right or there is a larger element on the left. And if any of the condition is not satisfied, then that element will not be found, so we'll not add it to the answer. But if both the conditions are satisfied, then we'll increase the count by 1. So let's just try this. So when we are at 2, we check that the minimum element from right till 2 should actually be equal to 2. There should not be any other element which is smaller than 2 and on its right. So we computed the minimum element from right, and we see that the minimum element till here from right is actually 1, which is smaller than the current element. So this implies that there was an element smaller than 2 on the right side. So one of our condition is not satisfied, we will not add it to our answer and our count will be 0. Now we will move to 1. So for 1, the minimum element from right to this element is 1. So that condition is satisfied. But we see that there is an element on the left which is actually greater than this element. So our second condition is not satisfied. So we will not increment the count by 1. Now we move to 3. So minimum element till 3 is actually equal to 3. So there is no other element which is greater than 3 and on the right side of 3. And there is no element which is there's no element smaller than 3 on the right side of 3, and there's no element greater than 3 on the left side of 3. So both the conditions satisfy, so 3 will be found using our binary search. By similar logic, 4 will be found, 5 will be found, and 6 will be found. So our total count will be 1. It will be increased by 1 at 3, then 1, it will be increased by 1 at 4, then at 5, then at 6. So our total count will be 4. So 4 elements we'll be able to find using this approach. So yeah, so they have not given the answer for this input. They have just shown that if we would have taken 5, we would have been able to find 5. So they have not given the exact answer for this uh, input, but the exact answer for this input should be 4. Now that we have discussed the whole logic and the intuition, let's quickly jump to the code. So this is the code for binary searchable elements problem. And one thing we have done here is that we have done one more optimization in terms of space. So the optimization that we have done in terms of space is that we were storing all the minimum elements up till this current element in an array, and then we were storing the maximum elements from left up till this element in an array. So what we are doing now, we are just storing all the minimum elements from right up till this current element, and for the maximum element thing we'll do that on the fly. So when we are traversing our array, we can calculate the maximum element up till that current element, and at this in the same step only, in the same loop only, at the same time we'll also check if it satisfies both the conditions. So while checking condition for each index on the fly, we'll also calculate the maximum up till then. So we would not need an extra space or an extra array to store the maximum for each index. So what we have done, we have first initialized our array which will be storing the minimum element from right up till this current element. So the minimum element we initialize with the last value, and for the last element obviously the minimum element is going to be the element itself. So we have just put the value there. Now we start calculating the minimum element from the second last index to 0th index. So every time what we do, the minimum element up till now, we take a min of the minimum element up till now in the current element, and we update this value, we store this minimum element value for the current index. So after this loop, finally our minimum from right variable or minimum from right vector will have the minimum value from right for each index. Now we are initializing a max element, and we have initialized with the first index or the 0th index. So for the 0th index, obviously there's no element before it, so the maximum up till now is going to be the element itself. And in this loop we'll be calculating the max element from left up till now, and also at the same time we'll be checking the two conditions and updating our answer. So this variable answer is going to store the final count. So we have started from index 0 and we'll be parsing the array. So at each element we calculate the maximum element up till now, and then we check the two conditions, that the maximum element up till now should be equal to the current element, and the minimum element from right up till now should be equal to the current element. If both the conditions are satisfied, as we discussed above, we'll do a answer plus plus, because this element will be binary searchable. And once we have done this computation for all the elements in the array, our answer will contain the final count and we will just return our answer. So let's try to analyze the space and time complexity. So this first loop where we are trying to calculate the minimum elements from right is actually traversing the whole array. So the complexity will be big O of n, where n is the size of the array. Again, the second loop is also traversing the array, complete array once again. So the time complexity for this loop is again big O of n. So the total time complexity of this complete solution is big O of n, and we are using a helper space or an extra space to store the minimum element till a particular element. So this vector is going to be of size n, where n is the size of the actual input. So we are using a helper space of size n, so our space complexity would also be big O of n. Now, as I said that I picked this question from Geeks for Geeks, so I wrote a solution and I submitted this solution on Geeks for Geeks. So these were some of the stats after submitting, and obviously the solution was accepted. So I hope you understood the intuition behind this problem, and I also hope that you understood why I was saying this problem is so important, because this problem attacks your understanding of the very basic concept of binary search, why binary search works. So if we are able to solve this problem, we also get a very clear or a very good understanding of why binary search works. So I hope you were able to understand the concept, the intuition, and the code. If you still have any doubts, to mention in the comment section and I'll try to address all your queries. And see you in the next video. Till then, take care, keep learning. Bye bye.